So in this video, I'll be explaining what are perceptrons. So perceptrons are very basic building blocks of artificial neural networks. These are the most fundamental computational units of artificial neural networks. You can think of it as an analogous to neurons in biological nervous system. In general, ANNs have very large number of neurons, as you can see in this diagram over here. An ANN having large number of neurons, but a most simple ANN architecture can have just a single perceptron as well. Before getting into the computation that is happening inside perceptron, I will try to start with a simple example. Let's say we want to predict whether a student will pass an exam or not. We are having two attributes over here. Attribute 1 is x1, where we have the value, that is the number of hours a student is dedicating in self-study. We have attribute 2, which is x2, where we have the value, that is the percentage of attendance of a student. So these are the two features that we are having over here, and using these two features we want to predict whether a student will pass the exam or not. We can solve this problem using logistic regression. So in logistic regression, we'll be simply having three weights, W0, W1 and W2. Why just three weights? Because we are just having two features over here, X1 and X2. If we have more number of features, then we'll be having more number of weights over here. Next, we will take the linear combination of our features X1 and X2. We'll be taking the product of X1 and X2 with the weights W0, W1 and W2. So first we'll multiply X1 with W1, we'll multiply X2 with W2 and we'll take the sum. The W0 over here is the bias term. So once we take this linear combination, we get an argument Z. Next, we'll apply a non-linear function, that is sigmoid, on the argument that we obtained in step number 2. This will give us a value P. This P will be having the value between 0 and 1. So what sigmoid activation function does actually is, it maps any value in the range of 0 to 1. So this is what exactly the sigmoid activation function is doing over here. Now since we are having P, if the value of P will be greater than 0.5, we will predict the student has passed the exam. If P is less than 0.5, we will say that student has failed the exam. So this is how logistic regression works. Definitely we'll start with some random weights W0, W1 and W2 at the very beginning. And then we'll keep on updating W0, W1 and W2 until we get a convergence where we'll be getting the best results. So how does this convergence and optimization of W0, W1 and W2 happens? For that you will need to get into the concepts of logistic regression. How do we calculate loss function and how do we optimize W0, W1 and W2 using the optimization. Now the computation that happens in Perceptron are very similar to the logistic regression that I have explained over here. So this will be clear with this particular diagram over here. So what we'll be doing is that we'll be having features x1 and x2. We'll be taking the weighted sum of x1 and x2 to get the sum over here. So we'll be taking the multiplication of x1 with w1, x2 with w2. That will give us the weighted sum over here. Then we'll apply a non-linearity or non-linear function on this weighted sum that we have calculated. That will give us the output y prime. The non-linear function that we are using in this case is again a sigmoid function. So you can see over here y prime is equals to sigmoid of w0 plus w1 x1 plus w2 x2. So this is the weighted sum that we calculated over here, and then we are applying a sigmoid non-linear function to get the y prime over here. In general, we'll be having n number of features. So the features could be from x1 to xn, and we'll be taking the linear combination of all this n number of features. Since the number of features are large, the weights that we'll be having will also be large. The weights will be w1, w2 up to wn and w0. and then we'll be applying a non-linear function on this weighted sum that we have calculated to obtain a final output, which is y prime. We can write it in a mathematical notation as I have shown over here. So in mathematical notation, we can represent this sum w1 x1 up to w1 xn as in summation over xi wi, where I is ranging from 1 to n. Then we are simply having w0. This g represents a non-linear function which is sigmoid in this case. So if I explain each term individually, so this is the linear combination of inputs as is written over here. This is non-linear activation function, as you can see over here, that we are applying. So in our case, non-linear function is sigmoid function, and y prime is the output that we are having. We can, once we have this mathematical notation, we can write this in the terms of matrices as well. So to get into the matrix notation, let me just define few notations over here. First we have X, which is a n cross 1 column vector. So in this column vectors, we are having the elements x1 to xn, where x1 to xn are nothing else but the features of our inputs. And next we are having a W, which is again a column vector of dimension n cross 1. It is having the weights w1 to wn. We can take the product of x and w by taking the transform of x. So x transform w will be our this matrix multiplication, and this is nothing else but it is same as this summation that we have calculated above. So we can just reduce this summation in the matrix notation to get this final formula for our single perceptron calculation, which is y prime is equals to w0 plus x transform w, and applying a non-linear function on this. Next, I will like to detail a bit more on the activation function or g that we are having over here. So this g, which is non-linear function till now, is called as an activation function. Till now we just talked about the sigmoid activation function because it is the most simple activation function which are very often used in neural networks, but we'll see there are more activation functions as well. The formula of the sigmoid activation function is simply this: 1 divided by 1 plus e to the power minus z. Let us see different activation functions we do have. So sigmoid activation function, as we have already discussed, it maps any input in the range of 0 to 1. Next, we have 10h activation function, which maps any value in the range of -1 to 1. Next, we have ReLU activation function. It has the value, it maps the value to the 0 if the value is less than 0. If the argument is less than 0, then we'll get output as 0. If the argument is greater than 0, then it behaves as a y is equals to x, a very simple linear line. Okay, so what is the importance of activation function? The importance of activation function, or the purpose of activation function, is to introduce the non-linearities into the network. I will try to explain this with the help of an example that we have over here. Let's say we want to build a neural network that can distinguish the red points and blue points over here. So basically we want to find a decision boundary that can classify whether a point belongs to this red cluster or the blue cluster. If we simply start with the linear activation function, if we build an artificial neural network with simple linear activation function, then we'll get a linear decision boundary. And you can clearly see that it will not be very efficient in making decision whether the point belongs to the red cluster or the blue cluster. Instead, if we introduce a non-linear activation function into our artificial neural network, our ANN can learn much more complex decision boundary which are non-linear in nature, and we can efficiently do the classification of this blue and red dataset. So this is all for this video. In next video, we'll be building much more complex artificial neural networks which will be having much more large number of perceptrons. Thank you.